Yes, okay. So we concluded that beyond the two population, we may have a situation where we can also be looking at measuring or trying to estimate the difference among more than what two populations. And if that happen, we can adopt the analysis of variance. But like I always tell you that it's not just the analytical tool, but we want to look at the assumptions, what is it, and how it can be applied. So let me give you, for example, if a ShopRite again want to look at whether there are three shops in three different malls in Ghana, whether they are performing well, are they performing the same, or they are performing differently. They can, based on the parameters in question, if they should take the population and want to um, uh, estimate whether there are differences in maybe sales or profitability, then they can adopt the analysis of what? Variance. So what we did is to go through all that. We're left with how to now apply it. So I'll pick an example and we'll go through nicely. I'm happy to inform you that beyond the manual way of analyzing the problem, if you have the data, we can also use Excel to model the problem and solve. Once we get the output, we should be able to interpret the results as well. So we'll be using the manual analysis, then we can look at how to also use the Excel to juxtapose what we would do using the manual calculation. Okay, so those charting, I want you to stop charting and let's focus on the discussion. Nobody should ask or post anything until I've asked a question. Please, otherwise I'll disable all the annotation for you guys. And once I do that, you may not be able to do anything online. Okay, so let's focus. So we've gone through what it is, the assumptions, and we agree that the first thing you should know that the populations in question must be normally what? Distributed, i.e. when you have more than two populations. Good. So we look at all this. I think I also explained that as far as the ANOVA is concerned, we need to also measure the hypothesis of the one-way ANOVA test, and we look at how to write the null hypothesis and the alternative hypothesis. We agree that the assumption is that, like I'm giving the ShopRite example, they may presume that all the three shops in the respective three malls or the four malls are performing the same. Means that we can say that the sales or sales in question or profit at these three different malls are yielding the same results. So the null says that all population means are equal. That is to say that mu1, mu2, mu3, they are all what's the same. So mu1 equals to mu2, mu2 is equal to mu3, all the way to mu what k. Then the alternative indicates that not all the shops in the Accra Mall are giving us the same net profit or the sales what volume. Means that at least one of them performs better than the others. So you see it's the alternative indicating that not all the population means are the same. That is to say that not all, at least one population mean is different from what the other. Means that mu1 may not be equal to mu2, or mu1 may not be equal to mu3. So if we go further based on the parameters we have from the population and we measure or do our statistical analysis, and we reject the null hypothesis, which says that all the means are what? The same. If we reject this, then it's now lie within our parameters to indicate that which of the population mean is different from what? The others. So unlike the two population where we just say reject the null hypothesis and we give our conclusion, for ANOVA, when we reject the null hypothesis and we give our conclusion, we must further go to check which of the population mean is actually different from the other. So we'll be looking at pairwise comparison. So I'll pick population 1 and population 2. Use some methodologies to check whether indeed they are different or they are what? The same. Then I'll pick another pair population, maybe mu1 and mu3, to check if they are the same or not. So ANOVA helps us to do all these analysis when we were trying to check to see whether like I'm giving the example with the ShopRite, if the Junction Mall ShopRite, Accra Mall ShopRite, and Achimota Mall ShopRite, these three, or we can also add the other one on the Kasua stretch, was the West Hills Mall ShopRite. These four, we can look at their sales performance and find out whether indeed the sales volume are different from each other or they are the same. If we agree that they are not the same, by comparing Junction Mall to Accra Mall, what is the difference? Are they the same or they are different? Or Junction Mall to that of what? West Hills, and Junction Mall to what? Achimota Mall. That is to say that we want to identify exactly where the differences is when it comes to the pair comparison. Okay. By doing that, we estimate, as I said, hypothesis. Good. Once we do that, I explain how to now do the analysis based on the type of data that you have collected. Okay. So we are going to look at these two, very important to be able to measure exactly whether we are going to reject the null hypothesis or we fail to reject the null hypothesis. We went through these ones and we concluded this was where we got to the summary of this table to say that if I pick the data, I need to be able to compute my sum of squares between groups, which we've explained earlier, and sum of squares within groups. Then we need their corresponding degrees of freedom. We defined what K is in our previous lecture, where we said that we are looking at the number of distinct population. So like the example, the 4 shopping malls, we have 4 ShopRite, okay? So this represents K, and they represent the distinct population. So Junction Mall, Accra Mall ShopRite, West Hill ShopRite, and Achimota ShopRite will become what? The K. K minus 1 will give me the degrees of freedom within, so D between DFB. Then N here is the sum of all the sample sizes from all the population. So we need to know how many samples do we have from the Junction Mall regarding the data collected in terms of sales. That of Accra Mall, we do the same. That of Achimota Mall and West Hills. When we put all the sample sizes together, that gives us what? Kn. That's the capital N here. We already know K. The difference here will give us the degrees of freedom within groups. Then, of course, if I want to know the degrees of freedom for total, the capital N here minus 1. Once I have these two statistics, I should be able to measure my means of squares between groups and means of squares within the groups. If I estimate these two, this guy here should give me what you call my F word computed. We are going to use the F distribution table for this discussion. So my F computed here represents the division between the means of squares between groups and means of square within groups. Once I've done this, I'm going to further look for what we call the F word critical, just as we've been doing for the T computed T table and that for Z computed and Z critical. This comparison would help us to know whether we are rejecting our null hypothesis or we are failing to reject the null hypothesis. So based on this, we can go further to pick a data and analyze it respectively. Yes, Sylvia, yes. Your hand is up. Yes, please ask your question.
Sir, good morning.
Yes, good morning.
Sir, please, could you kindly explain the one-way ANOVA table again? I just heard you say that we would use the table for today's discussion.
We use what?
We'll use this table, the one-way ANOVA table, for today's discussion. So please, can you kindly explain it again, please?
But that is what I'm trying to do. And your hand is up, means that you've not been listening all this while. It is good. The table just summarizes the way and manner we are going to compute the F computed, this guy here, based on available data. That is to say that all we want is to be able to find the F ratio here. And the F ratio is determined by the means of squares between the groups based on the data you have, divided by the means of squares within the groups or within the sample. Before you get this and this guy here, we need to estimate MSB, okay, means of squares between the samples that we have. And we've defined this, we did this last week. It's just, the table just summarizes what you have to do. Not to say that depend on the table to derive your, let me say, your answers or your solution. But systematically, before we can get F ratio, we need to define sum of squares between the samples and sum of squares within the samples. With this one, we estimated this by giving you the formula. And I remember saying that the sum of squares between groups, we are looking at the sample sizes for each of the groups with their respective sample mean. So you remember we said summation. Where is it? This guy here. Summation Ni goes to each of the sample sizes for each of the distinct population we have. Then X bar I also represents the sample mean for each of the respective population that we have based on the sample we've collected. X bar is the grand mean. And I remember saying that the grand mean is equal to the sum of all the means divided by the number of means. Sharon, Steven, can you please mute yourself or I will remove you from the group, please. You can't disturb us, sorry. So once this is achieved, so it means that I'm saying if I have 4 population, my X bar, okay, will be equal to X bar 1 plus X bar 2 plus X bar 3 plus X bar 4 divided by 4 because we have 4 sample means. That gives me my grand mean. The expression of this is what is expanded as, this is what we have here. So if I come to the table, I'm just saying that we need to define our sum of square between what groups based on the sample data that we have collected. Okay. Then we can proceed picking what a data, then be able to analyze this respectively. Any other question before we could continue? Any other question? Sylvia, are you okay now? Yes, Ayram.
Sir, some of us got the link so late, so we are not understanding anything.
You just have to follow. I can't be going back and forth. The link is even bad. The whole since morning I've been trying to connect. It's not going through. So please, I'll pick an example and we will take our time by way of explanation to facilitate the understanding as such. I hope that is clear for everyone. Yes, Sylvia, your hand is still up. What is the challenge? Oh, okay, your hand is not up. Yes. So all that I'm trying to advocate is that, so I go to ShopRite and I tell them we want to find out whether there is the need to know whether their sales performance for all the shopping malls in Ghana, each store differs from the other or they are performing the same. We can use a technique called the ANOVA, analysis of what variance. What are the assumptions before we can adopt this methodology or this statistical tool? We need to ensure that we've been able to meet all the assumptions. Then based on that, we can go forward to pick a sample from their sales respective to all the shopping malls. Then we can go forward. Abed, if you can hear me, let me ask you a question. So please unmute yourself. Abed.
Hello, sir. Hello, sir.
Yes.
I'm here.
I'm getting concerns that we didn't start this topic last week. Please, when I ended the two-way ANOVA, differences in population, did I start ANOVA statistical analysis?
Sir, that is what you said we will be starting with this week.
I said we will be starting this week with ANOVA. Did we start doing something before we ended the class? Because I have your recordings, and when I checked the recording, I just saw that we did up to a certain point. That's why I was asking you earlier, where did we end? Then we can start as well. But obviously, people are saying we did not start anything and all that. So confirm for me, please. Where did we get to? We were about ending and the network. Anyway, okay, so please pay attention. Can you stop asking that? It's okay, stop typing. Let's go on. So I've given an example about using the ShopRite issue. We ended our last discussion using two population to test whether significantly there are differences based on some parameters. So the discussion now is that what happens if we want to look at more than two population and we want to estimate whether there are significant differences based on, we can look at several factors that define these population. If that exists, we can use the Z and the T calculations in order to estimate these differences. So the analysis of variance is just to look at where we have three independent variables, or let me say three independent groups, and we want to verify or estimate whether there are significant differences that exist among them based on exactly what we want to achieve. My example to reiterate is that if we ShopRite want to look at significant performances, that's differences in terms of what sales volume at their various shops, giving cognizance to some factors, and they collect the data based on what has happened over a month or quarterly or yearly. As long as they want to test significant differences that exist among these three or these four shops in the respective malls, they can adopt the analysis of variance what 2. Therefore, we are expecting that we should be able to understand or recognize the situations in which we can use the analysis of what variance. Okay, if I can also look at over the past 3 years, I want to find out whether student performance in quantitative has been different over this 3-year period, or the performance is the same. I can use analysis of variance in this situation. So I may pick group 1 for first year, group 2 for second year, group 3 for third year. I'm still looking at what student performance across board, but we want to know the significance difference. Or can I write a report to say that student performance over these 3 years is the same or is different from each of the respective years? Okay, then I'm saying that I can apply the analysis of variance. Good. However, just as we've been indicating hypothesis testing for the 2 population means or a single population, what the ANOVA further gives us is the opportunity to identify if we want to do what we call pairwise comparison for the data or the groups that we have sampled. That is to say that if I reject the null hypothesis, which will be coming through now very soon, where does the difference lies in terms of what the data that we've collected? We are going to look at just one-way ANOVA test for this discussion. That's what we'll be looking at. We can also have the two-way ANOVA variance test with replication results. We won't be looking at that. We will be looking at just the one-way ANOVA. Okay. You can then make reference from these textbooks that we've provided. So what is ANOVA? Okay, or what is analysis of variance? So we say that it's a statistical technique that look at or try to estimate differences in means of more than 2 population. Once that is established, there are some assumptions that we need to bear in mind anytime we want to use the analysis of what variance, because you can't just pick any statistical tool to use. You should first of all identify whether it qualifies for the data that you have. Often I have students coming in, they've collected data and they don't know how to or which of the tools to use to analyze the data. My first question I ask them is that per the study that you are conducting, what exactly do you want to achieve? Because what you want to achieve, that is to say the objective of the study, will depend on the kind of data you have to collect, then the statistical tool to aid that data that you have collected. So the ANOVA, The first thing is that the data should be what? Normally what? Distributed. By now, we should all understand when we say the data is normally what? Distributed. Remember, if we do the normal distribution curve, the assumption is that data ranges from all this, or in the curve, we can have various data in continuum. Okay, so normally distributed. Then the sample, the population have what? Same standard deviation. That is, we are looking at the variance of the population should be what? Equal. We'll be looking at that in details. Then the sample observations are independent from each other. So if I go to Junction Mall and I'm collecting data for Junction Mall respect to ShopRite sales volume, it should just refer to volumes in what? Junction Mall. If I go to Accra Mall and I'm also collecting data, it should just represent the same as I have what? Collected. So data should be independent from each other. Sample observations are independent. Accra Mall data has nothing to do with what? West Hill Mall what data. You should bear in mind. Then the data measurement here specifically is numeric. That is quantitative. So it can either be interval or ratio. So please know that these assumptions defines the ANOVA technique before it can be used. Then in terms of conceptual overview, we are saying that if the population means are the same, their sample means would be closer together. That is to say that the more the sample means differ, the more evidence that we can use for the conclusion that the population means are not what? Equal. So please note that we are looking at sample means being differ from each other, because when you go further to measure the variances, there should be enough variability in the sample means that you've collected. So on that premises, we say that if the means of the populations are the same, there will be very few variability in the sample means. Then the test focuses on variation. So we are using, that's why we say the means of square between groups. We are looking for variation rather than what? Using just what? The means to verify the differences in that. Then again, if the variability among the sample means is small, it supports the null hypothesis. Otherwise, if it is large, it supports the alternative what? Hypothesis. So if you read further, you see more examples relative to this conceptual overview when it comes to the ANOVA. So the investigator controls one or more independent variable, usually called the factor or the treatment. Each factor again here contains two or more levels. Then we'll look at the experimental design. But because we are focusing on just one way ANOVA, as focus should be on this area or this slide to say that we want to evaluate the differences among the means of three or more population. Okay. For example, if we are looking at accident rates for first, second, and third shift, we'll be looking at data in relation to expected mileage for maybe 5 brands or 4 ties. But again, the assumption is the same as I indicated here. Population are normally distributed. Then the populations must have equal variance. And samples are randomly and independently what? Drawn. Once this is achieved, we can go further to perform our experiment. Okay. We may also have the randomized design. Okay. Then here, one-way factor or independent variable, we are looking at 2 or more treatment levels. Then we can go forward and do that. So if I'm able to estimate all these assumptions and in clarity, then we should be able to also identify the hypothesis for the one-way ANOVA. And here we are saying that for the null hypothesis, the assumption is that, in fact, there are no significant difference when it comes to measuring the population that we have collected based on the factor we are looking for. So if in terms of sales volume, we can conclude that, or the manager may conclude that, in fact, the sales volume across all the shopping malls are the same. There is not really a significant difference among them. So you have mean one may be the population mean for Junction Mall is equal to the population mean for Accra Mall, or the sales volume as well for Achimota Mall is the same, then that of West Hills Mall, let's say mean 4, is also what? The same. It means that there are no significance in terms of the sales that comes in either monthly or what? Quarterly. That is the null hypothesis. All population means are equal. Then the alternative hypothesis indicates that, in fact, not all the population means are what? The same. We can't conclude that the sales volume for Junction Mall is not the same as the sales volume for what? Accra Mall, similar to that of Achimota Mall and West Hills what? Mall. They are not what? The same. So if we reject the null hypothesis, then these now stand to say that indeed the sales volumes are not what? The same. Then the question is that if all of them are not the same, can we identify specifically which of the shopping mall sales volume differs from the other? So it does not mean that all population means are what? Different. It means that some pairs may be what? The same. So we do pairwise comparison. So I'll pick that of what? The Junction Mall, compare it to maybe West Hills Mall to see whether they are the same or not. And I'll be taking you through. We may end up to say that between Junction Mall and West Hills Mall, the sales volume is the same. What about between Junction Mall and maybe Achimota Mall, mean of, let's say, AC Mall? After estimation, we may conclude that the difference we are actually indicating is between Junction Mall and what? Achimota Mall, or maybe Accra Mall and that of what? West Hills Mall. Their sales volume are not what? The same. So for ANOVA, it's not just enough to say that let's reject the null hypothesis. It must go further to estimate where the differences really exist. And I said we will do what we call the pairwise comparison after we have rejected the null hypothesis. So please note that. Okay, and in that sense, we'll say that my hypothesis for ANOVA is just this way. Mean 1 is equal to mean 2, mean 2 equals to mean 3, all the way to mean what? K. Then we also state that not all the mean i's are what? The same. Good. So this is the null hypothesis, and this is the alternative what? Hypothesis, respectively, depend on where the difference actually what? Exists. So when we collect the data, we need to now go through the analytical procedure. And by doing that, we are going to look at what we call the variation. Archery, yes, your hand is up.
Yes, sir, please. So with the null and the alternative hypothesis is just displayed. And in some books, you will see that after they have written the null hypothesis, with the alternative hypothesis, they will either make it maybe H is to mean 1. It's not equal to I, mean or UI.
It's mean, not U.
Yeah, They will write it.
So if I get
alternative hypothesis,
you mean this one,
mu I is not equal to mu j.
Yes.
At least. So I hope you know what I'm talking about. So I just want to ask either.
That's why I'm saying that the mu I here, I goes to population 1, population 2, population 3, population 4. So maybe the other books are saying that instead of saying mu 1, mu 2, this could be I, J,
and the other one will be J,
K, and the rest. You get it?
And yes, and
let me land. So if I pick mu I, is the first population I want to compare to the second population, mu j. But this ij distincts the exact population you are trying to estimate the difference. So I goes to population 1, j goes to population 2, I goes to population 1, j goes to population 3, depending on the estimation. So please note that. Your next question, please.
So, Seb, they will write at least of pair into brackets, let's say 1, 2, 3.
It's assuming the same thing.
Oh, okay, sir.
It's the same thing. If I'm going to teach you guys again with research methods, you realize that I'll be restating the null hypothesis and alternative differently, okay? It's just to infer that it's the same statement we want to try to make. So you see, at least one of the mean is different from the other. It's just the same statement as that. Not all the mu I are what? The same. It's the same statement explaining the same thing that we want. It's just how it's being represented. Okay. In other books too, you see when I write mu 1 is equal to mu 2 is equal to mu 3 for the null, I also write alternative mu 1 is not equal to mu 2, it's not equal to mu or 3. It's the same statement being made here. So please note that. All right, so let's make progress if that is okay. Or any other question from anyone? Sylvia, is that okay? All right, Sylvia is absent. All right, so let's. Yes, I'm saying that I'm asking you, is it okay?
Yes, sir, I'm following.
Good. So after we have collected the data, now we have to go through the analytical procedure. So quantitatively, we need to now find out at what point are we going to reject null what hypothesis. And I'm saying that all we wanted here is to find what we call the F ratio, which we have named it as the F what computed, and also determine from our table our F what critical what value. We compare these two, then just that the decision rule is the same. If computed is greater than the critical, we reject what? The null hypothesis. So in order to find these F computed, we need to use, based on the data, estimate our variation within groups and between what? The groups that we have. So the important thing is to be able to define or address or estimate what is my sum of squares between what? The groups or the sample that I have what? Collected. And also be able to estimate sum of squares within the samples that I've collected. Indicating earlier on, I said we may manually go through this or use a statistical software. Just input the data inside, and if our data is correct, everything we have is correct, we just click on what? Solve, or we click on analyze, and within seconds, the software will just give us the outputs. Our aim is to interpret what's the output, but we are going to go through the manual way of doing this one first. Then when we finish, we'll take the same data. We may use just Excel. There are other statistical software we can use, but at this point, we are only going to apply Excel to be able to also solve the problem and interpret what the results. So please, let's go through together. If you have any question, you raise your hands and we can make progress. In the next 58 minutes, we should be able to solve a problem as well. So the sum of square between group is looking at the dispersions, that's the variation among the factor sample means that we have selected. Then the within groups also looking at the variation that exists among the data values within a particular factor level. So in partitioning of this variation, you may see in other books where SSB is also defined as SSA, sum of square among the groups, or SSE, but here we are looking at the sum of square explained, or you will just see among what groups what variation is the same SSB that we are trying to define. Then SSW, as we've indicated it here, can also be referred as SSE, but the E here is in terms of what error, or SSU where you have unexplained or just groups. So let's see how to now define. SST is simply the addition of what these two. So the focus should be on how to estimate the SSB and the SSW. So let me go through SSB quickly. Okay. We are looking at dispersion among the sample means. That's the SSB. Therefore, I need to be able to estimate the sample mean for each of the distinct groups that I have. If I do that, I should be able to calculate their respective grand mean, which is the X bar. Okay, if it is X bar, then the question is that what is the I goes to for group 1, group 2, group 3, like our friend is asking. So I goes to, or J goes to the respective groups. So if I need to know the sample mean for Junction Mall, sample mean for Accra Mall, sample mean for Achimota Mall, and sample mean for West Hills Mall. So I have 4 sample means. My X bar is the addition of all the means divided by the number of means I have based on the population. So I have this one, JM here, plus AM here, ACM plus X bar WM divided by 4, because I have 4 means. K is the number of populations. And here we are looking at the distinct number of populations we have. So if we are dealing with 4, then K represents number of population. This is 1, 2, 3, and 4. That is for K. We know NI represent the sample size for each population. So what is my sample size volume here? What is my sample size volume here? Sample size volume, sample size volume. So we have N1, N2, N3, and N4. That defines this. We talk about this. Remember, it's a summation. So I'm adding all the sample size, multiplying by the difference between the sample mean and the grand mean for each population square. Add all of them. That will give you my sum of squares between groups. Then I also need to know what we call the degrees of freedom for the dispersion among the sample mean. So my degrees of freedom for SSB is K minus 1. We've defined what K is already. If I'm able to know the degrees of freedom, which is DFB, let me name it as such, then I should go forward to compute my MSB, respective to dispersion between the sample mean for the groups should be equal to my SSB divided by my degrees of freedom between the groups. And that takes me to this point. Then I should be able to also estimate my sum of square within what groups. It's just to say, I always say, don't be confused with or alarmed with the formula you have here. We are only looking at what? With respect to each sample and their respective what sample mean. We are just squaring and adding them together. Okay, so we know what K is in this situation already. We know what Ni again, where I goes to 1, J goes to 1. That is the same sample size or the population we are looking at. We already know what X bar is. Xij here is each element for each of the sample under their respective what population. So if I come here and I say this is junction mall, sales volume, month 1, if we're looking at 12 months, January sales volume is 20, February sales volume is 30. These are the XIJs. Then I come to Accra Mall, January sales may be 25, February may be what, 30. So XIJ and Accra Mall is 25 and 30. The same to the other. So please note the XIJ. Where J measurement from what population, what I. So for each population, what are their respective what elements which represent the XIJ. Again, if I'm able to estimate my SSW, then we should be able to define my means of square within the groups, which is SSW divided by the degrees of freedom within groups. And that is also giving us N minus what? K. We've defined these elements already. If I'm able to estimate MSB and MSW based on SSB and SSW, then I can now estimate my F computed, which is MSB divided by MS what? W. So the table you see here summarizes step by step what I was trying to explain earlier. This goes all the way to define MSB, and this goes all the way to define what? SSB. Yes, Sylvia. Yeah, go ahead, Sylvia. Your hand is up.
Okay. Sir, please, the NI, is the previous slide.
Which NI? Where? NI where?
The sample size.
NI here. Yes.
You said it's the sum of.
I said it's the sample size for each of the distinct population sample you have.
Okay.
That is NI.
When we are adding everything together, when we are finding the sum, can we write it as nx bar 1 plus nx bar 2? Can we do it like that instead of n1?
This is it. This is it. This is the expansion. If you can see this, can you see this one? This is, so if this is my junction mall, this is for junction mall, this is for Accra mall. Sample size, respective sample mean, and the grand mean. Sample size. So each of them may be different from the other, but if they are the same, you move along as such. Those sending emojis, don't send anything. If you don't have any question, don't send anything. Yes, Aram.
So you said the XI and then XJ, they are used to denote for the means for x1, x2 respectively. So when you have xij, does that mean the mean of x1 times the mean of x2?
This, are you talking about this xij? Iram, is it this xij?
Yes, sir.
But I didn't say this is mean. I said the elements for each. Oh, my people. And I was giving this example. 20 is 20 is the xij here. 30 with respect to each of the sample. X bar, xi here. Again, you people, don't be confused because you see xi here. I said this is the sample mean. I goes to sample mean for sample 1 or population 1. I goes to population 2. I go to population 3. I goes to population 4, respectively. I here again goes to element I, element 1, element 2, element 3 is the same as J respectively. So that if we pick a data to analyze, this should simplify exactly what we want to discuss. Any other question before I pick an example with all the things I have indicated here? Any other question? All right, thank you very much. So the whole crust of our discussion is to be able to either say that we are rejecting the null hypothesis, or we are failing to reject what the claim that has been what put forward by using the F-force ratio. And this is the F ratio as I indicated earlier. Okay, we know all these already. Then the F statistic is the ratio of the between estimate of variance and within estimate of what? The variance. Then the ratio must always be positive. Please note that. I know someone will ask him why is it going to be, why is it negative? When we look at the table, you see why it should be positive. Then I've defined this one already. The ratio should be closer to 1 if HO is true. Otherwise, if HO is false, it should be greater than what? 1. Okay, so this is the data I want us to look at, to use it and see how we can be able to solve it. Okay, so we want to see if 3 different golf clubs yield different distances. So we randomly selected 5 measurements from trials on an automated driving machine for each what club. At 5% significance level, we want to know if there is a difference in the mean distances. Okay, so let's assume this is the data we have what collected. So maybe we went to the Achimota Golf Club, and this is what we have. We want to know whether there are differences in what? The distance in terms of what? When I'm able to hit the ball. What is kind of differences can we exist? So club 1, club 2, club 3, club what? This 1, 2, 3. Hitting the ball at each time. As I said, the data we've collected should be independent. Whatever is happening to hitting the ball with club 1 has nothing to hitting the ball with club 2 or that of what? Club 3. So if we have this, then we can go forward to measure all the statement I'm trying to what make. So let me pick my whiteboard quickly. Let's go through this peacefully. Okay, so let me write here ANOVA. ANOVA. So let me copy the question back. I have club 1, 254, 263, 241, and 237, 251. Club 2, CL2, 234, 218, 235, and 227, 216. Club 3, I have 200, 222, 197, 206, and 204. Okay. And if I have this, we want to know the significance difference. So HO and HA, as I said, as for writing the hypothesis for ANOVA, you should be able to get it. So we are saying that mu 1, so let's say mu club 1 is equal to, sorry. Is equal to mu club what? 2 is also equal to mu club what? 3. Then we can say that at least one of them is different from the other, or not all the mu i's, I goes to club 1, I goes to club 2, I goes to club 3 are the same. Okay, or you can also write it mu club 1 is not equal to mu club 2, also not equal to mu club what? 3. Doesn't matter, whichever one you write is the same. Okay, so let's go forward to, guys, I'm expecting a call. Let me pick it quickly. I'll come back to you. Sorry about this. Okay, thank you very much. Sure. Okay, guys, let's go on. So if I have this, I've stated my hypothesis. Remember, we need to define what? F ratio, or the F computed. MSB divided by MS what? W. But then we need to find our SSB, which is equal to what? Summation Ni x bar I minus what? X bar. That's it. I have 3 populations, so all I'm trying to do is this summation is trying to add, I'm going to look at what? N1 x bar 1 minus what? My grand mean plus N2 x bar 2 minus, the grand mean square plus N3 x bar 3 plus what? The grand minus the grand mean square. This is what I want to identify. Based on the data I have here, what is my N1, what is N2, and what is N3? Can somebody tell us? I've defined what Ni means already in the earlier statement. Any idea? Any idea? Yes, Abed, if nobody is talking, please speak. You're the classroom. Oh, so you are not paying attention. Mute yourself, my friend. Yes, Sylvia. Sylvia or Kofi Edu?
It's 5.
N1 is what?
It's 5.
N2 is what?
The same 5.
N3 is what?
The same 5.
Okay, McAfee or Matelvis, do you confirm this? Kofi, mute yourself. McAfee and Samoa. It's what?
Agreed, 5.
You agree, okay. So All right, so it's just simple. Look, just count the sample size. 1, 2, 3, 4, 5. So this is N1 equals to 5. N2, 1, 2, 3, 4, 5. N3, 1, 2, 3, 4, 5 is also what? 5. It's just to say that this is an even what? It's just simple terms. So N1 is 5, N2 is 5, N3 is 5. Okay. You may have different population sample size depending on the population in question. Okay, so please know that. Good. So we need to find X bar 1. We all know how to compute the mean, the sample mean for the population. So Sylvia, compute the sample mean for us. Matevis, compute the sample mean for club 2. Abed, compute the sample mean for club what? 3. Quickly. X bar 1, X bar 2, and X bar 3. Please calculate it for us. You should know how to compute sample mean. Sylvia, are you ready?
Okay.
Oh, just add and divide, that's all. And Ayiram, are you ready now? Yes. Yes, Sylvia, go on.
214 plus 263.
Do it. Don't tell me. Give me. We need the final value. Hurry up. Somebody has even done it. So 2. You said
so it's 241.2.
For which one?
0.2.
For which of
For the first one.
The first one.
Wrong. Please do it again.
Clap.
Do it again. Wrong.
I think it's 231.2.
Also wrong. Do it again. This is 214 plus 263. The third one is 241. This is 237, 251.
1.8.
I'm back again if you can hear me. The network is I hope everything is gone. Okay. So okay, let's do X bar 1 is what? X bar 2, X bar 3. Those who have done it, just give us the values and let's go on. So I have 249.2. Thank you, Don. What about the other one?
226.
226. Then this one is 205.8. So X bar would
5.8.
0.2 plus 226 plus 205.8 divided by 3. That should give you 227. That is my grand mean. So my sum of squares between to be equal to 5 plus 249.2 minus 227 plus 226 minus 227 plus 205.8 minus 227 square 5. Sorry. It should be equal to 4716.4. So we have our SSB. My degrees of freedom between will be equal to what? 3 minus 1, which is equal to 2. So my MSB is equal to 4716.4 divided by what? 2. What will I get here? Are you following, guys?
Yes, sir.
Okay, so this is 2.
Yes, sir. No, sir.
58.2. So this is MSB. I should take my time. The way the network is misbehaving, I need to finish. Okay, but I hope we are following up to this point. I just substituted what we have computed. Sample means we've defined it. Grand mean, we've defined it. We are now finding this. We know I explained the formula earlier. So N1 into bracket x bar 1 minus grand mean squared plus this. Then degrees of freedom for this is this. So my means of squared between the groups is 2358.2. Then we need to also find our sum of squares within what groups. This is where you have to do a lot. So what I always advise is that if you can define the sum of square within groups for each distinct population. Then when you finish, you add all of them together. Remember, it's x bar summation, double summation into brackets xij minus the sample mean square. Okay, this guy here. So we can find that for SSW for club 1, which is going to be what? I've cleaned the data. Let me copy the data here again. So I know we are saying that it's going to be what? Xij. So for this one, the first element is 254 minus what? The corresponding sample mean for club 1 is 249.2 square plus the next Xij for club 1 is 263 minus 249.2 square plus the next one is 263 minus 249.2 square plus 263. Sorry, this is 241. The next one is 237 minus 249.2 plus 251 minus 249.2. This will give me the sum of square for just club 1. Then I can also define sum of square for club 2 based on the xij's I have here. I have 234 minus 226 plus 218 minus 226 plus 235 minus 226 plus 227 minus 226 plus 2. Somebody should do SSW for club 1 for us quickly based on the information I have. This is 241. This one is 216 minus 226 again square. Then I can calculate SSW for club 3. Again, this is 200 minus 205.8 plus, let me write it here, 222 minus 205.8 plus 197 minus 205.8 plus 206 minus 205.8 plus 204 minus 205.8 square. So this is just to say that I'm breaking them down. I need a sum of square within groups for club 1, club 2, club 3 respectively. Okay, so somebody is giving for club 1, I have 432.8. Okay, I hope, Matelvis, I hope we are good to go. that for, okay, so let's do that for club 2 and club 3 respectively. Let me erase this side. I may not need this, guys, anymore. Oh, guys, you have calculator, do this quick. Don't be slow. Club 2, okay, somewhat, I have 310, okay. Uh, 310, okay. That's what someone gave us. And that for club 3, the last one, because we need to know club 3 quickly. My people, please make it quick. Some of you don't participate at all in class, but those who are participating, I'm noting you. Some of you, all you want is, let's try the solution and go. Yes, Matelvis, can you do the last one quickly? Or Ayiram or Abed or Kofi or the rest. Please do this quickly. I can't really see. Okay. The first one is 222 minus 205. Start from 200 minus 205. Isn't clear. Okay. This is 200 minus 205.8 square. This is 222 minus 205.8 square. This is 197 minus the same 205.8. This is 206 and this is 204. Okay. I hope it is clear now. Please do it quick. Hey. Which is which? Matelvis, you are having, oh, now I have 3 conflicting figures. 130.5, 486.6, 376.8. Which is which? Another one say 466.4. 376.83. Okay, so 376.8. Now we can add.
Yes, 376.8.
So add this figure plus that figure plus this figure. So our MSW will be equal to, what is the total? Good, 1119.6 divided by, remember, degrees of freedom within is what? N minus what? K. What is N? N, as I said, is the number of sample size. So how many sample size? For club 1, we had 5 sample size. Club 2, 5 sample size. Club 3, 5 sample size. So that is 15 minus 3. So this will be equal to what? So this will be 93.3. Good. So if I have this,
I get 99.97.
99.97. Why is it Joy FM? Confirm again, please. It should be 93.3. Yes, those who hands are up. What exactly do you want to? Hey, this internet. Theodora, yes. Theodore, what's your question? Your hand is up, so when I call you, be quick about
Please,
it.
I was about to answer a question. Sorry.
Okay, Sylvia, what about you? Is your hand is also up. Okay, so if we have this, let me go to the next. So my F ratio, or I said F compute, be equal to MSB, MS what? W. MSB was 2358.2, 93.3. Okay, so I have 25.275. So this is my F what computed. Good, good, good. Now I need to also define my F what critical. Please note that just as we were using the distribution tables for the others, we are using the F distribution table for ANOVA problem. Okay, means that we need to estimate alpha. So F will be equal to degrees of freedom, F critical, degrees of freedom between, degrees of freedom within, and alpha here. Alpha is given as 0.5. So degrees of freedom within is 2. Sorry, between is 2. Degrees of freedom within is what? 12. Alpha is 0.05. We use the F distribution what? Table. So let me pick my table for F distribution. I'll share the table with you later. Let's see, F distribution table. Good. So let me share my table. Okay, so this is the table. Okay, so please watch here. This is the F distribution table. We are looking at the first row. You have numerator degrees of freedom. That is the degrees of freedom between the groups D, F, B. Then you have denominator degrees of freedom. We are looking at degrees of freedom within. So if I have degrees of freedom between to be 3, okay, and the denominator degrees of freedom is 5, giving alpha to be 0.025, I'm here as my DFB is 2, DFW is 5. The area in the upper tail has been given as this. So for F distribution, we are only looking at the area within the upper tail. We are not dealing with anything that has to do with what? The lower tail. So if this is 0.05, which is also given as this, then just as we've been doing horizontally, I'm moving all the way under what? 3. And vertically to I move all the way under 5, but the degrees of freedom is this. So my F critical is going to be what? 7.76 for this example, using 3 and what? 5. Our example is 2. Our question is degrees of freedom between is 2. Degrees of freedom within is 12. Alpha is 0.05. So our F critical is going to be 3.89. 2, 12, alpha is 0.5. Move closer to the point of intersection is 3.89. Do you follow?
Yes, sir.
Yes, sir.
Yes, sir.
So reading the table shouldn't be difficult.
Yes, sir.
All right, please mute yourselves now. Good. So let's go back here and now come to, so this is equal to 3.89. If that is so, F computed 25.275 is greater than F critical, which is 3.489. Then the same decision rule, we have to reject the null hypothesis. Then we make our conclusion to say that once we've rejected the null hypothesis, it says that the differences, there is a significant difference in the mean distance for the 3 golf clubs. Okay, there is a significant difference in the 3. I should go over the table. Oh, Charlie, let's move forward. I said, so this is my table. This is my table. If DFB is 10 and you have DFW to be 20, alpha is 0.05, 10 and 20, alpha 0.05. What will be my F critical value? This is 10. DFW is 20, is also here. Alpha is 0.05, is also here. I'm walking, let me say walk from Tamale to Bechem, Kumasi, Takrady, Accra, Tema, all the way to University of Ghana, Legon. This is where we have met. So you are meeting your girlfriend or your boyfriend on campus. You are going through all this. I hope that makes it clear. So 10, you are starting here. 20, you are here, moving all the way along to meet up here. So my degrees, my F critical is what? 2.35. Good. Emmanuel, I hope it is okay now.
Yes, it's clear, sir. Thank you very much.
So as I said, we've rejected the null hypothesis and we have to now go further to conclude that the mean difference in terms of distance among the golf clubs are different from what? Each other. That is our conclusion. But the next question is that if we conclude that there are difference, which is mu 1, that's club 1, is not the same as club 2, not the same as club 3. It may not be the case that all of them are not the same. So can we also say that if they are all the same, where are the differences? So I need to do pairwise comparison. Compare mu club 1 to mu club 2 distance. Then club 1 and club 3. Or club 2 and club 3. So we are looking at pairwise comparison to indicate exactly where the differences exist. So I'll compare these two, whether there are or they are not. It's possible there will be difference or there is no difference. I need to estimate this. And by that, we are adopting two, or we can use two different procedures to do that. The first one is the 2K Kramer. Can use the 2K Kramer procedure. So please note that. This is just to say that we want to tell which population means are significantly different from the other. For instance, can I say that mu 1 is equal to mu 2? But so I'm talking about the club, but club 2 distance is not the same as that for what? Club what? 3. Or can I say that club 1 is not equal to club 2, but club 2 is equal to club what? 3. So I have to go through the procedure to do these differences I have indicated here. And that is what I said, it's called a pairwise comparisons of what? The mean. So we want to know exactly the absolute mean difference with a critical what range. And by this procedure, we compute what we call the critical what range, which says that I have Q alpha here. Q alpha, we are looking at the value from the standardized range table. So we'll be using the table to estimate Q alpha times the square root of MSW divided by 2. We already know what MSW, or multiplying 1 over Ni plus 1 over N for J, where I goes to, and J and I goes to what? The sample sizes from the population's levels. Okay, so depending on, if I'm comparing 1 and 2, if I'm looking at population 1 and 2, I goes to first population, J goes to the second population, respective to the other. But remember, our sample size are the same. So I can just assume I and J are 5, the same. So I don't have to change anything. Okay. So when we are done with this critical range, we are going to compare the critical range value with the absolute mean difference. So this is mu1, mu2. The difference between these two, I'm comparing this first one, what is their absolute mean value? Then I also determine the absolute mean value for mu1 and mu3. Then I also have to compute the absolute mean value for mu2 minus what? Mean what? 3. I'm comparing these two. This is the pairwise first. I'll compare the value of the absolute mean difference for this pair to the critical range to understand whether indeed the differences exist here. I also compare the absolute mean difference for these two pairs, these two guys here, to the critical range, then this pair to the critical range. Based on the values for each of them, then we can say indeed the difference is here or that or this. So please note that if the absolute mean difference is greater than the critical range, then we say that indeed between these two, mu1 is not equal to mu2. So the difference exists here. So when the absolute mean difference for each pair is greater than the critical range, then our conclusion will be that the differences exist between those two pairs that you have, the two pairs that you have indicated. So please note that. So let me go forth to, now we know the sample mean for X bar 1 club. Yes, Aram.
So, is the rule the same? Because you are saying if the absolute difference value is actually greater, then it means there's a difference. So can we say the rule is also the same in this scenario?
I can't hear you, Aram.
So I said if the absolute mean difference value is greater than the F critical, then we are saying that then there's a difference between these mean variables.
Please. I didn't say F critical. I said critical range. And this is the estimation for critical range. We are not talking about F critical here. I hope you follow. We are not talking about F critical. We've moved from that point. Yes, Austria.
So, sir, with the normal hypothesis, I mean the double with the ANOVA, our conclusion will be based on the absolute we compare. I mean the comparison. I'm trying to say that unlike the other ones we did, as for this one, our conclusion is going to be based on the absolute we take. Is it correct, sir?
No, no. I'm saying that our conclusion is that when we reject a null hypothesis, then our conclusion is that not all the means are what? The same. That is your conclusion. But it is not just enough to say that not all the means are what? The same. Can we identify where exactly the differences exist? For example, as I was giving the Accra Mall example, look, if I'm able to do that for Junction Mall, all of them, and we say they are all not the same, then we go further to say that let's compare where exactly is the difference. Is it between Accra Mall and Junction Mall and West Hills, or Junction Mall and what? Achimota Mall? That gives a better clarity to say that indeed, if management want to now look at where should we put our energy into to realize more sales, or where should we put more people in terms of what? Sales volume, we should rather consider between what? Accra Mall and West Hills Mall, because they may not be the same. Sorry, they may be the same. If the sales volumes there are the same, what can we do differently to attract more customers in order to increase what? Our sales volume for each of the respective what? Shopping mall. So it is not just to say that they are all not the same, but we want to know exactly where the differences what exist. Autry, is that okay?
Okay, so with the example you just gave, what it means is that when the absolute is greater than the critical point, sorry, is it critical range?
Critical range.
Yes, when it is greater than the critical range, what it means is that it will be more prudent to invest more at that area.
You can say that it is. Okay, it will be prudent to invest there because between ShopRite and between Junction Mall and Accra Mall, their sales volumes are not the same. Okay, can we increase it? But if between Accra Mall and Achimota Mall, the sales volume is the same, what can we do differently? So there could be what if, like the sensitivity analysis. What if, or what can we do to improve it or improve that? So let's move forward. Therefore, I need to estimate the pairwise comparison between, let's look at Club 1 and Club 2. What is the sample mean for Club 1, X bar 1 minus X bar 2? Okay, that is to say we've already computed 249.2 minus 226.0. This is equal to what? 23.2. Then X bar 1 minus X bar 3. The absolute mean difference, we are looking at 249 minus 2.2 minus what? 205.8. Also, we are looking at the absolute mean difference. Then we can do pairwise for X bar 2 and X bar 3. It's also equal to, we are looking at 226.205.8. X bar 3. Yes. So let's find the absolute mean difference. Now, how do we read the Q alpha? Okay, let me show you. As I said, we'll use a standard table to read Q alpha. Okay, and we know alpha already. Okay, what we need to know, we use a different table. I'll share that one with you as you can see it in your slide. So Q alpha this is the table for using the Q alpha. We need to know D1 and D2, degrees of freedom between degrees of freedom within. Degrees of freedom between is 2. Degrees of freedom within, sorry, D1 here. Okay, so we are looking at the Q value from the table indicates J, K, and what? N minus what? K. K is 3, remember. K is 3, that is the distinct population. N minus K here, this is 12. So 3 and what? 12. 3.77, that is our Q alpha value. Okay. So that is 3.77. By substitution, we have 3.77 times the square root of what? MSW was 93.3 divided by 2 times 1 over 5 as 1 over 5. This should give us what? 16.285. Our time is up. But please note that have you been able, this should be 23.2. Okay, this is the value. This one is 43.2, and this is 20.42. So please watch here. You realize that the compared between sample 1 and sample 2 is 23 greater than the critical range. So we'll say that mean 1 is actually not equal to mean 2. This is also greater. Our conclusion is that all the absolute mean difference are greater than the critical range. Therefore, there is a significance difference between each pair of means at 5% level of what? Significance. I will continue the other one, the Fisher LSD test procedure, when we meet on Thursday. But just to say that these two procedures, if we want to do pairwise comparison after we have rejected a null hypothesis, we go through this procedure and